Give a large language model and an unconstrained loop, and you are one hallucination away from an infinite execution cycle and a massive API bill. OpenWorker, built on the Python package coworker, offers a distinct solution. It is a local-first, provider-agnostic desktop agent platform. Developed under the guidance of Andrew Ng's team at MIT, it approaches agent stability with a highly opinionated architecture. It entirely rejects the complex multi-agent swarm setups currently dominating industry discussions. There are no independent peer agents negotiating tasks here. Instead, OpenWorker secures its production environment through three specific constraints: a single mathematically bounded loop, a risk-aware execution dispatcher, and strict application layer allow lists. Yet, to achieve this, the platform completely ignores standard safety practices like operating system sandboxing and context window compaction. To understand how this works, we will trace the exact data flow of a single user message from intake to completion. Studying a production agent harness requires evaluating the systems it controls and the explicit technical debt it chooses to accept. Messages from a text interface, command line, or IDE funnel into a single FastAPI control plane. This server routes requests to the TurnEngine. Build engine slots the selected persona into the engine. Personas are configuration data classes. Chat, code, and cowork share this identical loop. Inside TurnEngine.loop, the execution order is absolute. Before any API call is made, the engine checks its hard iteration cap, defaulting to 150. If the cap allows, the system streams a model turn, executes any requested tools, appends the results, and loops. The cycle ends when the LLM returns an assistant turn containing 0 tool calls. There is no explicit completion tool. Done is an implicit state. Checking the cap at the top provides a hard ceiling. The system trusts an implicit termination because infinite execution is structurally impossible. Once the LLM generates a batch of tool calls, the engine enters the execution phase. Instead of running tools sequentially or in parallel, OpenWorker uses a risk-aware mixed dispatch, splitting batches into 2 lanes. A _parallel safe gate routes low-risk actions, like reading files, to fan out concurrently. State-mutating actions, like writing to disk, bypass this gate into a strict chronological queue. This execution layer is also where we see the system's only subagent, a tool called Explore. It is structurally non-recursive and hard-capped at 10 iterations. Simply put, a subagent cannot spawn another subagent. This mixed dispatch model solves a crucial timing problem. It maximizes speeds for data gathering while strictly preserving the intended side effect order for dangerous mutations. While common heuristics limit LLMs to 12 tools, OpenWorker uses a registry of over 159. It manages this through progressive disclosure. The initial prompt receives a lightweight catalog. The heavy tool bodies and schemas download on demand, only when called. Once a tool is called, it hits the permission engine, the final gate before execution. Every action undergoes rigorous application layer checks. The engine evaluates requests across 5 distinct approval modes, ranging from read-only to full access. If authorization fails, the TurnEngine does not crash. It utilizes a deny and continue loop, appending an error message and allowing the LLM to learn and retry. By combining progressive disclosure to keep the prompt clean with strict application layer allow lists, the harness scales capabilities without overwhelming the LLM's context window. While the application layer defenses are robust, the system makes explicit, highly visible engineering trade-offs. The first gap is isolation. There is no operating system sandboxing. Tools like run shell execute via raw subprocess.popen, inheriting the full parent environment without any containerization. The second gap is context management. The entire historical message array is forwarded to the provider on every single turn. There is 0 text compaction and no token counting, introducing a high risk of silent window overflows during long sessions. Furthermore, the system lacks in-loop code verification to check its own work, and it relies on a flat SQLite database with 0 memory eviction routines. Facts written once live forever. These omissions are calculated bets. The creators wagered that perfect application layer authorization is sufficient for a local desktop environment, treating OS-level isolation and context compaction as unnecessary overhead. The OpenWorker architecture relies on a core triad: a single mathematically bounded loop, a risk-aware mixed dispatcher, and heavy application layer allow lists. This stability is achieved by explicitly accepting the technical debt of uncompacted context history and bare metal shell execution. Real-world system architecture requires choosing exactly which risks you are willing to engineer away and which ones you are willing to live with.